Hi, this video is going to cover section 5.2, which is the addition rule and complements. The learning objectives are to be able to use the addition rule for disjoint events, be able to use the general addition rule, and then also compute the probability of an event using the complement rule. So first, let's use the addition rule for disjoint events. So two events are disjoint if they have no outcomes in common. Another name for disjoint events is mutually exclusive, right? So in other words, using set notation, E intersect F is equal to the empty set, right? So in other words, if this is true, then we can say that E and F are disjoint or mutually exclusive. Right, so it's just another term. So we can use Venn diagrams to represent events as circles enclosed in a rectangle. So the rectangle represents the sample space, and each circle represents an event. So for example, suppose we randomly select chips from a bag. Each chip in the bag is labeled 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Let E represent the event, choose a number less than or equal to 2. And let F represent the event, choose a number greater than or equal to 8. So these events are disjoint as shown in the figure, right? So notice there's no overlap between events E and F, right? So here we're just calculating the probability of event E and probability of event F, right? So let me try to do this, right? So the probability of E would equal the number, the number of items in event E divided by the number of things in the sample space, right? So that equals, so if we look at E, there's three numbers in here, right? 0, 1, 0, 1, and 2. So we put 3 there. And then there are 10 things total in the sample space, right? So it's 3 out of 10, which is 30%. And then if we go to calculate the probability of F, there's 2 numbers in F and 10 in the sample space. So that's why we take 2 divided by 10 and get a probability of 0.2, right? So then the next one is looking at the probability of E or F, right? So remember, I could show this as the probability of E union F, right? So the probability of E union F is equal to the number of things in E or F divided by the number of things in the sample space. So if we look here above, there's 3 things in E and 2 things in F, so there would be 5 things in E union F, right? Because E union F would equal the numbers 0, 1, 2, 8, and 9, right? So we're just joining, joining those two events together. So we get 5 out of 10, which is equal to 0.5, right? So notice that this is also the same thing as if we just took the probability of E plus the probability of F, right? Which would be 0.3 plus 0.2, which also equals 0.5. So, and this only works if we have disjoint events, right? We're going to look at it in the next learning objective if the events aren't disjoint, right? So the addition rule for disjoint events is if E and F are disjoint or mutually exclusive events, then the probability of E or F equals the probability of E plus the probability of F, right? So in other words, we could say the following, right? We could say, if E intersect F equals the empty set, then the probability of E union F is equal to the probability of E plus the probability of F. Right, so it's just another way to write that, right? So the first part's telling us that the E and F are disjoint events, and then just showing that equation and using the union symbol instead of or. Right? So then here below it says the addition rule for disjoint events can be extended to more than 2 disjoint events. So in general, if E, F, and G ... each have no outcomes in common, they are what we call pairwise disjoint. Then the following is true, right? So the probability of E or F or G or ... equals the probability of E plus probability of F plus the probability of G, right? So in other words, so in other words, we can extend this to as many disjoint sets that we have, right? So they have nothing in common. All right, so then I have another example, the addition rule for disjoint events. So the probability model shows the distribution of the number of rooms and housing units in the United States. So the number of rooms and housing units, we have the options 1, 2, 3, all the way to 9 or more. And and then we're seeing the probability for each of those. So part A is that we want to verify that this is a probability model, right? So remember, to verify this, we have 2 conditions for this to be a probability model. We want the probability of each event to be in between 0 and 1 inclusive, right, for all I, right? So in other words, if I let one room be E sub 1, 2 be E sub 2, 3 be E sub 3, and so forth, then what we have is we have 9 possible events, right? So we want to verify that all of the events, right, are going to be in between 0 and 1, right? So if we look through all these values, they're all in between 0 and 1, so we're good, right? So that checks out. And then the second condition is that the sum of all of the probabilities has to equal 1, right? So if you take out your calculator and you add up all these numbers, that sum does in fact equal 1, right? So that checks out, right? So that's the check that we have to go through to verify that that's a probability model. So then part B says, what's the probability that a randomly selecting housing unit has 2 or 3 rooms, right? So what's important to notice about this probability model is that it's not possible to have a housing unit that has 1 room and 3 rooms, right? It's every housing unit has to fit into one of these categories, right? It can't, there's no overlap, right? So in other words, all of these events are going to be mutually exclusive or disjoint. So in part B, when I'm finding, what's the probability a randomly selected housing unit has 2 or 3 rooms, right? So, probability that we get a 2 or 3 rooms, this would be equal to the probability of having something with 2 rooms plus the probability of 3 rooms, which would be equal to, so plugging those values in from the table would be 0.032 plus 0.093. Right, so if we add those up really quick, right, we get 0.125. Right, so then part C, we have what is the probability a randomly selected housing unit has 1 or 2 or 3 rooms, right? So this would be the probability this would be the probability of getting a 1 or 2 or 3, which would be equal to the probability of a 1 plus probability of 2 plus probability of 3, which would be equal to, so grabbing this from the table would be 0.010 plus 0.032 plus 0.093. So adding those together, we get 0.135. right? So now what we want to do is look at the general addition rule, right? So what happens when you need to compute the probability of two events that are not disjoint? So suppose we are randomly selecting chips from a bag again, but each chip is still labeled 0 through 9. Let E represent now that we choose an odd number, and F represent the event that we choose a number less than or equal to 4. So E would equal 1, 3, 5, 7, 9, and F would equal 0, 1, 2, 3, 4. So notice that E and F would be equal to 1 and drawing a 1 and a 3, right? That's what's common. So in other words, these events are not disjoint, right? Because if they were disjoint, they wouldn't have anything in common. The intersection of E and F would be the empty set. So you can see here, some labeling here. So the overlapping region is E and F, right? So this region here is E and F, and then the shaded regions represent E or F, right? So all three of these regions here represent E or F. So the problem is if we just calculated this using the probability of E plus the probability of F, we're going to count the numbers 1, and 3 twice, essentially, right? So what we're going to have to do is subtract that out, right? So it's saying we can compute probability of E or F directly by counting because each outcome is equally likely. So there are 8 outcomes in E and F and 10 outcomes in the sample space. So the probability of E or F would be the number of things in E or F divided by the number of things in the sample space, right? So there's 8 numbers in E or F, right? So if we count these numbers here, right, count all of those, we get 8 things, and then there's 10 things total in the sample space. So 8/10 is equal to 4/5, right? But if we use the addition rule for disjoint events that we just did before, we're not going to get 4/5, right? So in other words, the probability of E or F would equal the probability of E plus the probability of F, which in this case there's 5 things in E and 5 things in F, so it'd be 5/10 plus 5/10, which equals 1, which is not true, right? Those are not equal. So notice the slash to the equal sign here, right? So our result is incorrect because we counted the outcomes 1 and 3 twice, like I mentioned, right? So to avoid this double counting, we have to subtract out the probability corresponding to the overlapping region, which is the intersection, right? So in other words, the probability of E or F is going to be equal to the probability of E plus the probability of F minus the probability of E and F, right? Get rid of that double counting. So you would have 5/10 plus 5/10 minus 2/10, right? And we get the 2/10 because there's 2 things in common, right? So the probability of E and F would be 2/10. So if we combine those, we get 8/10, which equals 4/5, which that agrees with our original result that we found just by counting, right? So this general addition rule shows what we're talking about, in general, right? So in other words, the probability of E union F is equal to the probability of E plus the probability of F minus the probability of E intersect F, right? So that's in general. So we don't have to worry about if the things are mutually exclusive or not. We can just use that rule, right? And if they are mutually exclusive, this probability is just going to be 0, right? Because if they're mutually exclusive, E and F is equal to the empty set, right? Which means that probability of getting something in there is 0 because it's not possible, right? So that just kind of shows that this rule works, for mutually exclusive events as well, right? It's just the one we shared before is more specific, right? If we know the events are mutually exclusive. So here's an example. So we're calculating the probability using the general addition rule. So we're given that the probability of E equals 0.32, the probability of F equals 0.61. We want to find the probability of E or F if the probability of E and F is equal to 0.1, right? So we're just going to use that equation for the general addition rule and plug in what we know, and we can simplify that, right? So the probability of E union F, E or F, is equal to the probability of E plus the probability of F minus the probability of E intersect F, right? E and F. So this would be equal to, so 0.32 is the probability of E, plus the probability of F, which is 0.61, and then we would subtract out the probability of E and F, which is 0.1. Right, so that, if you throw that in your calculator, that's equal to 0.83. Right? So now it says, if probability of E equals 0.32 and probability of F equals 0.61, so like before, we still want to find the probability of E or F, but we know that E and F are mutually exclusive, right? So the probability of E or F is equal to the probability of E plus the probability of F, right? In this case, because they're mutually exclusive. But if you wanted to, you could still use that general addition rule, because as I mentioned, this statement here means that E and F is the empty set. So in other words, the probability of E and F is going to equal 0, right? It's not possible. So this would be equal to 0.32 plus 0.61 still, but we would have minus 0, right? So that's equal to 0.93. Right? So then now what I want to do is use the addition rule with contingency tables, and these are also called two-way tables. Right? And what these tables do is it essentially gives you a count in different categories, right? So like if I look at this number here, 68.5, right? That is the number of males that are also married, right? And these numbers are all in millions, right? So there's 68.5 million males that are married, right? And so what this table describes is it gives us a summary of the marital status of males and females aged 15 and older in the US for 2019, right? So if you want to write that down, we can. So this shows the marital status of males and females 15 years and older in the US, right? So US residents. Right, and it shows here it's 2019, right? So this is for the year 2019. Right. So something that's often done with the two-way table is we want to find totals, right? So we want to total the columns and the rows, and also find the total number of people combined, right? So I'm going to take a screenshot of this and work on this off to the side so I have a little more room. Right, I think maybe what I do is I'll just erase this part that I had written here. I should have enough room. That way we can see the table and the questions all together. Right, so we want to basically add a row, call this the total, and add a column for total. right? So if I add up all the numbers in the males, right? So take 45.3 plus 68.5 plus 3.5 plus 10.7, we get 128, right? So that's the total number of males, 128 million. And then if I add up the female column, I get 135.6. And then next I want to add up the rows, right? So the never married, I'm going to take the 45.3 and the 40.1, add those together and get 85.4. Right, so I'll do that for all the rows, right? So I'm adding the male and female numbers together for each of the marital statuses, so I get 80. So for the next one, for married, I get 137.8. For widowed, I get, what, 14.9. For divorced, I get 25.5 million. And then, you know, what goes in this box here would be the total number of people total, right, males and females. So it should equal, you know, the 128 plus the 135.6, and then it should also be equal to adding up these row totals as well, right? So, you know, you can kind of double check, but they both equal 263.6 million. Right, so there's 263.6 million people total in this data, right? So part A is to determine the probability that a randomly selected U.S. resident 15 years and older is male, right? So we want to calculate the probability of randomly selecting a male, right? So that's going to equal the number of males divided by the number of things in my sample space, right? Which would be equal to 128 over 263.6. I don't have to worry about writing like the millions down because everything's in terms of millions. So when I take millions divided by millions, those just go away, right? So to make it easier, I won't write that because it's not it doesn't impact anything here. So when you do that, you'll get approximately 0.4856, right? If you want to write that as a percent, that would be 48.56%, right? So then part B, right? Part B is that we want to calculate the probability of randomly selecting someone who's widowed, right? So the probability that someone's widowed, selecting someone that's widowed, would be equal to the total number of people that are widowed divided by the number of things in the sample space, which would be equal to, so that 14.9 number, right, that we found, right? So that's this number, this value here, right, that I highlighted in yellow, and that's divided by the total things in my sample space, which is the 263.6 number. So this is approximately equal to 0.0565, which equals 5.65%. Right, so then part C is to determine the probability that a randomly selected U.S. resident 15 years and older is widowed or divorced, right? So the events widowed or divorced would be mutually exclusive, right? Because you can't be widowed or, widowed and divorced at the same time, right? Maybe you were divorced before and also a widow at one time, but your marital status is you're in just one of those categories, right? So these are mutually exclusive, right? So in other words, being widowed intersect divorced would equal the empty set, right? So these are mutually exclusive. Right, so the probability of being widowed or divorced, union divorced, would equal the probability of being widowed plus the probability of being divorced, which is equal to right? So we would have to take the number, the number of total number of people that were widowed, which was the 14.9 we just found above, and divide that by 263.6, and then looking at the total number of people divorced is 25.5, so that's going to go on the top, divided by 263.6 people total, right? And so we have two fractions we're adding with the same denominator, right? So I could just add their numerators together and keep the same denominator, right? So that would be, so 14.9 plus 25.5 is 40.4, and that's over 263.6, and that number comes out to be approximately equal to 0.1533, which is equal to 15.33%. Right, so that's the probability of randomly selecting someone who's widowed or divorced. Right, but then part D, it says determine the probability that a randomly selected U.S. resident 15 years and older is male or widowed. Right. So note in this case, it's possible to be male and to also be widowed. Right. If you look up in the table, we have 3.5 million of those people. Right. So, this is just a visual way to show why we need to subtract out the probability of being widowed and male, because this number 3.5 is going to be in this total, right, of males, but it's also calculated in this row total, this 14.9 number for the total number of widows, right? So that number gets counted twice, so that's why we have to take one away, right? So what this would be equal to, so the probability of being a male or being widowed is equal to the probability of being a male plus the probability of being a widow minus the probability of being a male and widow, right, which would equal, so the total number of males is 128 million, so that's divided by the 263.6, and then plus, so the total number of widows was 14.9 divided by 263.6. So then now we're looking for that 3.5 number, right, which that represents the number of males that are widowed. We have to subtract that out, so we'd have minus 3.5 out of 263.6. Right, so just remembering that 3.5 is added in this number and also in this number, so we don't want it twice. We want to count those people just once, so that's why we have to take it away. So this would be equal to, so if you simplify these fractions, right, add and subtract, we get 139.4 out of 263.6 million, which this is approximately equal to 0.5288, which is equal to 52.88%. Right. All right, so now we're ready to talk about the very last learning objective in this section, which is the compute the probability of an event using the complement rule, right? So the complement of an event, so if we let S denote the sample space of a probability experiment and let E denote an event, the complement of E denoted E raised to this, C, right? Like E C superscript. That's all the outcomes in the sample space S that are not outcomes in the event E, right? So the idea with this complement rule is, how's the probability of E and the probability of E complement related to one another, right? So how they're related is they have a sum of 1, right? So in other words, if I take the probability of E plus the probability of E complement, that gives me 1, right? So then if I subtract the probability of E from both sides, what I get is that the probability of E complement is equal to 1 minus the probability of E, right? Which is this equation that's up here, right? And you might wonder, why is the probability of E plus the probability of E complement equal to 1, right? So you're basically saying, like, let's say you were rolling a die, six-sided die, right? Six-sided die. Maybe E is the event that I roll a 1, right? So I'll just say roll a 1. So E complement, right, would be equal to, you know, rolling a 2, 3, 4, 5, or 6, right? Those are all the possibilities that are not in E, right? Because E would just be equal to the set with just 1 in it. So, you know, the probability that one of these things is going to happen is going to be 1, right? So if, you know, either I roll a 1 or I don't roll a 1, right? One of those things has to happen. So that's why the probability of E plus the probability of E complement are going to equal 1. Right? So you can see this is just a diagram showing you. So the green circle is E, and then everything outside of the circle would be E complement, right? Those would be all the things that are in the sample space, but not in E. So we got two examples around this. So according to the American Veterinary Medical Association, 31.6% of American households own a dog. What's the probability that a randomly selected household does not own a dog, right? So if I let D equal the event that a household owns a dog, right, then D complement would be that they don't own a dog, right? So they don't own a dog, right? So that's what we're after. So the probability of D complement would be equal to 1 minus the probability of D, right, using the equation from above. So this would be equal to 1 minus, so this 31.6% as a decimal would be well, not 0.0, excuse me. It would be so 0.316. Right? So I would just take 1 minus 0.316, which equals 0.684, which if you want to show that as a percent would be 68.4%. Right? So the probability of an American household not owning a dog would be 68.4%. All right, so then the next one, we have an example where we're computing probabilities using complements again. So the data to the right represents the travel time to work for residents of Hartford County, Connecticut. So we have various travel times here, and we have frequencies, right? And notice if we read through this, all of these events would be mutually exclusive, right? There's no overlap, in other words. So it says, what is the probability a randomly selected resident has a travel time of 90 or more minutes, right? So we could calculate the relative frequency, right, to find that probability. So the probability of, so we'll say, you know, let event E equal the event that we need to commute. 90 or more minutes. Right? So the probability of E would equal, so if we look at 90 or more minutes, that is 4,895 people in that, right? That's the frequency. So if I take that number and divide it by the total, the sum of the frequencies, I'll get the relative frequency. So if I add all these up, you should get a total of 393,204. Right, so that number would go here. So this comes out to be approximately 0.0124, right? Or as a percent is 1.24%. Right? So then now for part B, it says compute the probability that a randomly selected resident of Hartford County, Connecticut will have a commute time less than 90 minutes, right? So less than 90 minutes would be like E complement, right? So in other words, all the others, right? So, you know, I don't necessarily want to have to add all those up, right? That seems maybe a lot of work to do. So an easier way is use that complement rule, right? So we could say the probability of E complement would be equal to 1 minus the probability of E, which would be equal to 1 minus that 0.0124 number, right? Which equals 0.9876, which is equal to 98.76%. Right? All right. So that's all I have for this section. Let me know if you have any questions. Thanks.